All right, we're going to do some problems in chapter 22. All right, I'm going to start with 2250 next. All right, so UPAC name, and so it is tungsten, like CO, is that an 8? It's an 8, okay. CO8. All right, so that one we won't do our, it's a square anti-prismatic. That is not one of our choices. All right, so we have a carbonyl. We have 8 of them. We have octa carbonyl, and then tungsten. Carbonyls are neutral, so it's just tungsten 0. So octa carbonyl, tungsten 0. That is very strange. All right, so if we did an electron count, tungsten 0 on the periodic table, you find tungsten. Look at the column, and the column number on top is a 6, so that would be a D6, and this would be a 16 0. This would be a 22 electron complex. Very strange. All right. We name whatever they put in front of us. All right, so we have in part B, we have a CO, H2O, sub 2, En, sub 2, and then in brackets, so then outside the brackets, we have SO4 sub 3. All right, so SO4 is a sulfate, which is -2. So you have to know SO4 is sulfate, it's -2. We have 3 of those, so that's -6. So that makes this complex a +6. Water is neutral, ethylene diamine is neutral, so the cobalt is a cobalt 6. So cobalt 6, if you want the d electron count, you find cobalt on the periodic table, which is number 27. The number above it is 9, so that is a D3. All right, and so we have diaqua. Then we have 2 ethylene diamine. Since the name ethylene diamine has a Greek prefix, we have to use bis ethylene diamine. And then we have cobalt, and then that is 6. And then sulfate. All right, and so if we want the coordination number, we have 2 coordinations for the 2 waters, but remember ethylene diamine, 1 ethylene diamine coordinates in 2 spots. All right, and so coordination number is 6 because we have 4 for the 2 ethylene diamines and 2 for the waters, and so we are octahedral. And your water is a weak field ligand, your ethylene diamine is a strong field ligand, and so it would be a low spin. And so if we put in our D3 in our octahedral, it would just be here, and you would have the D2sp3 hybridization since the 2 orbitals on top are empty. All right, and part C is a potassium. Is that another 8? CN8. All right, MO, and then CN8. All right, so this is a potassium, octacyano molybdate. Now you got to figure it out. You got your potassium, which is +1. There's one of them. You got your cyanides, which are -1. You've got 8 of them. That means MO has to be a +7. So it's potassium octacyano molybdate 7. And then part D, you've got your CrO4 -2. All right, well, that's just chromate, but they want you to name it probably as something other than chromate. So chromate would be the name of that polyatomic ion, but if we're naming it using the rules, we have a tetraoxo chromate, and then this is a 4 oxygen, so that's -8, so this has to be a +6, and so that's chromate 6. All right, so tetraoxochromate 6 would be the way you would name it as a complex, but CrO4 -2 is chromate. All right, go to 52. All right, give the structures for these. We have diaqua, dicyano-copper 2. All right. Got your, all right, so you got your diaqua, dicyano, copper 2. So this is copper 2 because you have 0 for the charge there. Cn is -1, so that's -2. So the copper has to be a +2. If we're doing the coordination number, that is 4. 2 for the 2 waters, 2 for the 2 cyanos. And so we have to then have our copper, that is 2. Look at the number up top of the copper, it is 11. So copper 2 is D9. And so when your coordination number is 4, you are going to predict tetrahedral. The only time you're going to predict square planar is if you have a D8. So any other D electron count with a coordination number of 4 is going to be tetrahedral. And if we put in our 9 electrons, so tetrahedral is the opposite of octahedral. It is 2 on bottom and 3 on top. Tetrahedral is always a high spin. And so when you put in your 9 D electrons, you have a paramagnetic 1 unpaired electron. All right, so then total electron count would be your D9 plus your 8, 2 water ligands is 4, 2 cyanide ligands, also another 4, that's your 8. This would be a 17 electron complex. And hybridization for tetrahedral is always sp3. All right, let's try B. Potassium hexachloroplatinate 4. All right, so this one you got to figure out how many potassiums that you need. Hexachloroplatinate 4. Platinum, and now you have a hexachloro. All right, and then we know that this is a +4. We know that is a -6. We know it is a neutral compound. That means we have to have 2 potassiums. And so you would put a K2 in order to get a +2, or 3, I don't know. a +2 here and a +4, which is +6, and -6 is your neutral compound. All right, so again, here your coordination number is 6. It's going to be octahedral. These are weak field ligands, so this is going to be high spin. And a platinum 4, you look at platinum on the periodic table, the number above it is 10, so that is a D6. And so for high spin, for octahedral, 1, 2, 3, 4, 5, and 6. And so this is high spin because the CLs are weak field ligands, and so it is paramagnetic with 4 unpaired electrons. When you do your total electron count, you got your D6 plus your 12 ligand electrons from the 6 CLs. This is an 18 electron complex, which is predicted to be a stable compound. All right, part C, tetraamine nickel 2 perchlorate. All right, tetraamine. And then a perchlorate, so you have ClO3 minus is chlorate. Remember, when you add an oxygen, then it is a perchlorate. So ClO4 minus is a perchlorate. And so that is a ClO4 minus, but they tell us that the nickel is +2. And we know our NH3 ligand is neutral. And so we have to have 2 of them. In order to have 2 of them, we then put a sub 2. You don't put the negative there. ClO4 sub 2. All right, and so here you've got nickel 2. The number above nickel is 10, and so nickel 2 is D8. Coordination number is 4, and so that's when we predict a square planar. All right, and so then you have your splitting pattern for square planar, and it is always a low spin. Doesn't matter what the ligands are, if you are square planar, you are low spin. Now, these are strong field ligands, doesn't make any difference as far as high spin or low spin. If you are square planar, you are low spin. All right, and so you have your D8 plus your 8 ligand electrons. You have your 16 electron complex. And all square planars that you're going to predict will be 16 electron complexes, diamagnetic. All electrons are paired up. All right, part D, tetraamine platinum 2. So it says a platinum 2. So this is +2, this is 0. And then a tetrachlorocuprate 2. So they tell us this is +2. We know that the CLs are minus, so that's -4. All right, so overall we got a +2. Overall we got a -2. And that is our complex 452D. All right, 54. Any of the following octahedral complexes display geometric isomers, draw the structures, label them cis-trans. So, okay, you got your CO, and then you can have your NH3s 180 degrees away, which is your trans, and all 4 of your NO2s. All right, so this is your trans, where your NH3s are 180 degrees away, or you could write it with your NH3s 90 degrees away, and this is your cis. All right, and so because the complex had a negative charge, so you put in brackets to show that it is still a negative charge. All right, so that's A. All right, so B, no cis trans. All right, you have 5 of one thing and 1 of another. Doesn't matter how you put it in there, they're all exactly the same. Part C, all 6 of them are exactly the same, and so in part C, there are no cis trans. And then part D is again no cis trans. All right, so you have to have 2 of the same, well, doesn't have to be the same, but is going to be the same, that you can put 90 degrees apart or 180 degrees apart in order to get a cis-trans isomer. All right, 58. Using crystal field theory, okay, so how many unpaired electrons? So ZR Cl6 minus 4. All right, so that's chlorine, which is minus 1, 6 of them, that's minus 6. So you have ZR, that is a plus 2. All right, so you have 6 Cl, so your coordination number is 6. That makes it octahedral. Your chlorine are weak field ligands, and therefore it's going to be high spin. All right, so then you just have to find ZR on the periodic table and look at the number on top of that column, and that is a 4. And so ZR2 is D2. All right, and so you have your octahedral, and you put in your 2 D electrons. And so this is paramagnetic, has 2 unpaired electrons. All right, if you did the total electron count, you would have the D2 plus the 12 electrons from the 6 chlorines, and this would be a 14 electron complex. You would not predict that to be stable. We only predict 16 and 18 to be stable, but that very well could be a stable complex. I believe it is. All right, but we don't predict it to be stable unless it is 16 or 18. All right, part B. OSCl6 minus 2. All right, coordination number again is 6. It's octahedral. Cl, these are your weak field ligands, and so it's going to be a high spin. So that's minus 6. So your osmium has to be a plus 4. Plus 4 minus 6 gives you the minus 2. Find osmium on the periodic table. Look at the number on the column on top, and that is an 8. And so osmium 4 is D4. All right, and so it is high spin. So we put in our 4 electrons as the electron goes to the higher orbital. Higher energy orbital is a high spin. So this is paramagnetic, and it has 4 unpaired electrons. Unless, of course, the problem says it's low spin. All right, so this one says it is low spin. So you predict a high spin because it's a weak field ligand. But if they tell you that it is low spin, All right, so just because we predict it doesn't make it 100% correct. Right? We are predicting it because of the ligands, but if they tell us, that means that they did their experiment and found that it was paramagnetic, but there were only 2 unpaired electrons. So when they find that information, then they know that it is low spin. All right. Now the next one is the prediction and the actual is the same, which is the usual case. Part C, Mn Cl6 minus 4. All right, coordination number is equal to 6. It's octahedral. All right, and so you have a weak field ligand, and so you predict high spin, and then you actually see that, yes, they labeled it as high spin. All right, and so you have your -6, your Mn has to be a +2. You find your manganese on the periodic table. The number on top of that column is a 7. All right, so Mn2 is a D5. All right, and so when you have your high spin and you are D5, all 5 electrons are unpaired. So this is a paramagnetic with 5 unpaired electrons. All right, and so the hybridization is sp3d2. So if there is 1 or more electron in the 2d orbitals that are higher in energy, then it's sp3d2. If they are completely empty, then it's d2 sp3. All right. Number 60. All right, so we have a platinum, NH3 sub 2, NO2 sub 2, and that's +2. So diamine, dinitrito, platinum, 4, because your NO2 is the nitrite, because we know nitrate is NO3 minus, ATE, nitrate. So this is nitrite. All right, and so as a ligand, it is nitrito. All right, so that's -2. This is neutral. This has to be a +4 in order to give an overall of a +2. And so your platinum 4, you look at the periodic table, the number on top of the platinum is 10. That is a D6. The coordination number is 4, 2 for the NH3, 2 for the NO2. All right, and so since this is a not a D8, it's a D6, we predict tetrahedral. Although I should read the problem, yeah, so either, no. So they give us more information to determine. All right, so tetrahedral, all tetrahedrals are high spin. So that is 2 on the bottom, 3 on the top, and 6. 1, 2, 3, 4, 5, and 6. So this is 4 unpaired electrons. All right, but it says that there are 2 unpaired electrons, and this is where the book should be more consistent. All right, and so as I said, your square planar, the one that they gave us, looked like this, but these two are extremely close in energy. And so we should actually be writing it like this. And then it's always low spin. And that's how you get 2 unpaired electrons. So they should not be showing it this way if they're going to ask a question like that, because the answer, if they're going to show it this way, is you're going to have low spin here, and you're going to have unpaired electrons 0, unpaired electrons 4, and they say it's 2. All right, and so we're going to stick with our square planar should be looking like this, not 2 on the bottom and then 3 going up. All right, and so since there are 2 unpaired electrons, 4 if it was tetrahedral, 2 if it is square planar, and the answer is it has 2 unpaired electrons, and so your answer is this is square planar. All right, and so square planar has a hybridization of DsP2. All right, MnCl4 minus 2. Part B. All right, that's minus 4, that's plus 2 to give an overall of minus 2. Mn plus 2, the number on top is a 7. So Mn2 is D5. Coordination number is 4. All right, and so we put in our D5, and we have our choice. It's either going to be tetrahedral or it's going to be square planar. Tetrahedral is always high spin, and so you would have 5 unpaired electrons. Square planar is always low spin, and so you would have 1 unpaired electron. So here is the splitting pattern for tetrahedral. Tetrahedral is high spin. It doesn't matter what the ligands are. This is square planar. This is low spin. Doesn't matter what the ligands are. They are weak field ligands. But if it's square planar, it's low spin. If it is tetrahedral, it is high spin. And this one has 5 in parentheses. That means it has 5 unpaired electrons, which means that it is the tetrahedral with the 5 unpaired electrons. And then part C, NiCl4 minus 2. So that's minus 4. That's got to be plus 2 to give an overall of a minus 2. All right, coordination number is equal to 4. Again, you're going to find your nickel 2. Find nickel. The number on top of nickel is 10, so nickel 2 is D8. All right, so then you put in your tetrahedral 8. You put in your square planar 8. If it is tetrahedral, it has 2 unpaired electrons and it is paramagnetic. If it is square planar, it has 0 unpaired electrons and diamagnetic. And this one says it has 2 unpaired electrons. And so this one is the tetrahedral. If we were going to predict, we would have predicted square planar, because anytime you have a coordination of 4 and D8, the high percentage of those are square planar. Not all of them. This one is tetrahedral. And the hybridization for tetrahedral is sp3. All right, AuF4 minus. That is part D. All right, so you've got your minus 4, you got your plus 3. In order to get an overall of minus 1, you find your gold on top of gold. It is number 11, and so gold plus 3 is D8. All right, and so we would have to draw the exact same pictures as we drew up above. We have our tetrahedral, and we have our square planar, and we put in 8. Again, tetrahedral is always high spin, and it would have 2 unpaired electrons. Your square planar is always low spin, and you would have 0 unpaired electrons, and for this compound it said 0 unpaired electrons, and so it is square planar. And that is DSP2 for the hybridization of square planar. (2262) COEN3 plus 3. All right, so here ethylene diamine is no charge, so you've got your cobalt 3. You find cobalt on the periodic table. The number on top of the cobalt is 9. Cobalt 3 is D6. Ethylene diamine, there is, for each ethylene diamine, you get 4 electrons and no charge. All right, and so that is a plus 12. We have an 18 electron complex. Your coordination number is equal to 6 because each EN has 2 coordination sites. So it is coordinated off of each end. So 1 ethylene diamine is 2 coordinations. So it is octahedral. Right? So on this one, you would need a chart. You would have a maximum absorption at 470. What color do you expect from this ion? All right, so again, have that picture. So you got to go to the chart. All right, and so we are, the absorption's at 470, so we're right here, right around 480, and so what we're going to see is orange. And so you go to as close as you can get to 470 on this chart and see that the color is going to be orange. So you got to, this chart would be given, you don't memorize the chart. So if the wavelength is 470, you're going to observe, you're going to see an orange. Depends on what the question is. What color is absorbed? Blue. What color do we see? Orange. All right, and so what color do you expect for this ion? This ion is going to be orange. All right, 2264. All right, COEN sub 3 plus 3. Yellow. Let's see, 3. All right. But CO F6 minus 3 is blue. All right, so this is a strong field ligand. And this is a weak field ligand. All right, and so when we go back to our chart and look at yellow, what we see is yellow. All right, when we see yellow, we have a wavelength of 430. All right, and so again, the smaller the wavelength, the higher the energy, and so that is a high energy. All right, and then when we changed it to the fluorine, so that the shift went to, now we see blue. And so blue is 610 nanometers, a longer wavelength and lower energy. All right, and so your weak field ligands are going to have a lower energy absorption. Your strong field ligands are going to have a higher energy absorbing. All right, and so that is a predicted shift. When you have strong field ligands, you have your high energy wavelength absorbed. Remember, your strong field ligands are going to have more energy because they are low spin. All right, so these are both coordination number 6. They are both octahedral. The difference is you have a strong field versus a weak field. So your strong field looks like this. Your weak field looks like this. All right, and so both of these, your CO is a +3, so cobalt is 9 on top. So both of these are D6. So the strong field is going to be a low spin because this fourth electron will not go way up here to this high energy. It's going to pair. The pairing energy is lower than the delta. All right, and so your delta is very large. All right, so here you have your 6, and it is high spin because you have weak field ligands, and so it goes up here because your delta is very small. And so it would be higher energy to pair than it would be to go up that small amount of energy. And so your D6 is here. All right, and so remember your energy, delta is energy, which is equal to HC over lambda. Your delta is equal to your energy, that's equal to HC over lambda. All right, and so a small energy is going to have a larger wavelength. And this is going to have a smaller wavelength. And so when you look at the picture, you see your smaller wavelength. All right, so your larger energy, that's yellow, that's the strong field ligands. Your larger wavelength, your lower energy, that's your blue, that's with the weak field ligands. All right. That was 64, 66. What is the value in kilojoules per mole for delta? So delta is energy, that's equal to H nu, which is equal to HC over lambda, when your wavelength is 680 nanometers. All right, and so you have your delta, which is your energy, which is equal to HC over lambda. So H is Planck's constant. It will be given 6.626 times 10 to the minus 34 joules times seconds. C is the speed of light. It will be given 2.998 times 10 to the 8th meters per second. What you will have to do is to convert your 680 nanometers to meters. Wavelength has to be in meters so that it will cancel the meters here. All right, and so your wavelength is 680. Instead of putting n, I'm going to put what n equals. That is 10 to the minus 9 meters. And then I just plug it into my equation. 6.626 times 10 to the minus 34 joules times seconds. 2.998 times 10 to the 8th meters per second. So my seconds cancel. Divided by 680 times 10 to the minus 9 meters cancel. And then I'm left with joules. So when I push the button, I get joules. All right. All right, but we want our units, it says in kilojoules per mole. So this energy, when I push it, this is the energy of a photon. So this is joules per photon. All right, and then we're going to take our joules per photon, and we have to get the kilojoules per mole, is what the question says, give the units in kilojoules per mole. So once we get that number, after we push the buttons here, in order to get to kilojoules, we have to get rid of joules. And K is 1 times 10 to the third, so we have to divide by 1,000. That's a J. So joules cancel joules, and now we would have kilojoules per photon. We want per mole, and there are 6.022 times 10 to the 23rd photons in a mole. And so the photons cancel the photons, and now you will have it in the units, kilojoules per mole. All right, so when you push the buttons here, you get 4.38 times 10 to the minus 19. And when you put in your 4.38 times 10 to the minus 19, divide by 1,000, multiply by Avogadro's number, you get I think 264 kilojoules per mole. Right. I do know that those numbers are correct, and when you stick that in there, I'm not sure. All right, so your energy there is energy of a photon, and it wanted it per mole, and so you had to use Avogadro's number, and the units you had were joules. You had to convert that into kilojoules. All right, let's try 2268. Zn H2O sub 4 plus 2 is colorless. Zn H2O sub 4 plus 2 is colorless. Explain why this might be expected. All right, and so your coordination number here is 4. All right, and so your Zn, this is 0, so Zn has to be plus 2. So Zn, which is plus 2, you look at Zn, the number on top of Zn is 12, and so Zn2 is D10. All right, and so plus the 8 ligand electrons, this is an 18 electron complex, and it would be predicted to be tetrahedral. Well, actually, if it is D9 or 10, it is always tetrahedral. I've never seen a D9 or D10 be a square planar. All right, now the question is, why is it colorless? And so it is a tetrahedral. All tetrahedrals are high spin. All right, and to get color in your very colorful transition metal complexes, they are very colorful because the electrons will go back and forth in your d orbitals. Now it can be no movement of electrons. This is completely full. So no electrons can move. For an electron to move, you would have to put 3 electrons in one of these orbitals, or you would take an electron out completely of the d orbital, and it wouldn't be a d to d transition. It would be d to some other orbital. All right, and so the electrons cannot go back and forth inside here because it is a full d subshell. So anytime you are D10 or D0, you would predict it to have no color or so it's either going to be colorless or it will be white. If you are a D10 or a D0, that's what you predict. Of course, that's not every case, but that is the predicted case. Anytime you are D10 or D0, you would be colorless. So that's the end of chapter 22's homework. 24, and we got to 24. We can do a couple of problems in chapter 24. All right, so 24.3. All right, so ethylene glycol. So that is a CH2, CH2, and then you have an OH on both ends of your ethylene glycol. Adipic acid. Adipic acid has a C double bond OH. It's got a carboxylic acid on both sides. In the middle, you've got CH2 sub 4. Then you have another C double bond O and OH. All right, and so what's going to happen is you're going to do a Fischer esterification. You're going to make an ester. You take the OH from the carboxylic acid. You take the OH from the carboxylic acid. You take the H from the alcohol. And so you're going to have your O and then CH2, CH2, O. Now this O is connected to C double bond O. You have your CH2 sub 4 and C double bond O. And that is going to keep going and going and going. And so when you have your polymer, that is N is a large number. So you're going to have N amount of this, you're going to have N amount of that, and you're going to get N number of these polymers. Plus, you're going to get a bunch of H2O. That is the condensation reaction. All right, so you have to be able to lasso your water in order to get your condensation polymer. All right, 24.9. All right, what is the difference in structure of D-ribose versus 2-deoxyribose? All right, so ribose is one you have to know the structure of. So D-ribose is a pentose. It is an aldopentose. And all the OHs are on the same side. All right, so it's got an aldehyde group, pentose because it has 5 carbons, and O's because it is a sugar. So that is ribose. Deoxyribose is on carbon number 2. So you have your OH, but now this and this, both sides of that one are H. So deoxyribose, you took a oxygen, so instead of having OH here, it's simply an H. You removed that oxygen off of carbon number 2. All right, 17. Amino acid. So an amino acid, and the ones that we are looking at are the alpha amino acid, which means the carbon here is the alpha carbon. The carbon next to the C double bond O is the alpha carbon. All right, so you have to have an amino group, and you have to have an acid group. All right, or called a carboxyl group. All right, so that acid group, this is a carboxyl group. So you have to have an amino group and a carboxyl group. On 18, this is just multiple choice. On 18, example of an addition polymer, that's rubber. Your bonding responsibilities for linking 2 strands for DNA. So the GC and the AT are together because of hydrogen bonds. GC has the 3 and stronger. The AT has the 2 hydrogen bonds, a little weaker. And then, of course, for number 20, the complementary base for G is C, so guanine is cytosine. All right, we will do the rest of that homework tomorrow.